Hello, everyone, and welcome to today's event brought to you by ColdQuanta and Classiq. We're talking about scalable quantum computing here. My name is Yuval. I'm Chief Marketing Officer for Classiq, and together with me are three wonderful experts. Paul Lipman, who's President of Quantum Information Systems at ColdQuanta. Hey, Paul.
Hey, Yuval. Good to be here.
Professor Mark Safman, who's the Chief Scientist for Quantum Information at ColdQuanta. How are you doing, Mark?
Hi, Yuval. Happy to be here.
Happy that you are here. And Nir Minerbi, who's my boss and also the co-founder and CEO of Classiq. Hi, Nir.
Hey, Yuval. Hi, all.
So today, as the industry moves from prototyping to production, and as companies all over the world get more and more serious about quantum computing, the question of scalability, how do you get something that runs on many qubits? What does it take hardware and software-wise? Why is it important? These are all the topics we're going to cover in today's session. We're going to divide this into approximately 4 parts. First part, we're going to talk about, after brief company presentations, we're going to talk about why should I care? What can I do with 100 or 200 or 1,000 qubits that I couldn't do today? The second topic is going to be, why is it difficult? Why is it difficult to get to a larger number of qubits? Why is it difficult on the hardware side? Why is it difficult on the software side? The third question is, why now? How do I get started? Is it available? When it will become available? And so on. And of course, we're going to leave plenty of time for audience Q&A. There is a Q&A button on the Zoom link that everyone has, and I encourage you to submit your questions at any time, and I'll try to incorporate them into the presentation as much as I can. So, Paul, why don't we start with you? Would you mind giving us a few minutes introduction about ColdQuanta, who are you, and what do you do?
Yeah, sure thing, Yuval. So ColdQuanta is a quantum company, by which I mean we are certainly developing a quantum computer that we'll talk about extensively today. We also develop advanced quantum sensors for precision navigation, precision timing, and sensing, and a variety of other quantum technologies. And really at the core of all of that, though, is the modality. So the modality that we are specializing in is cold atom and ultra cold atom. We design, develop, and manufacture glass cells exactly like this one that I'm holding up here in front of the camera. Fits in the size of the palm of your hand. And then within that cell, we use lasers to trap atoms, cool those atoms down to a hair's breadth above absolute zero, and then manipulate the quantum state of those atoms, both for the purposes of creating, say, a quantum sensor, but also to perform qubit operations. The company was founded in 2007, so we've been in business for quite some number of years and have built a great depth of expertise, a really terrific team of scientists. We're headquartered in Boulder, Colorado in the US. We have offices also in Madison, Wisconsin, which is where Professor Safman is based in Oxford in the UK, and looking at opening other locations around the world in the very near future.
Excellent. Thank you very much. And Nir, would you mind giving a few-minute introduction on Classiq and what we do?
Yeah, definitely. So Classiq is a quantum computing software company. We are based in Israel and employ over 30 quantum software engineers and quantum information experts. And basically, we have one goal, and the goal is to make scalable quantum computing software possible. Currently, it's, and I'll show it in a few slides later on, it's doable if you want to do that for 5 qubits, challenging if you want to develop software for 20 qubits, and practically impossible if you want to scale. And this is what we solve, I guess.
Great. Paul, do you have a few slides you'd like to share, perhaps?
Well, we have maybe 1 or 2, which Mark will share shortly, that talks a little bit about some of the things we're doing here in advancing the science and the engineering of cold atom quantum computers.
Excellent. So Nir, go ahead. I think you wanted to share a few slides.
So I guess we are here to discuss scalable quantum computing. And let's start with the software. And obviously, we are not here to explain why quantum computing is important. We all know that, we understand the potential, and we want to make it possible. And in order to make it possible, it's a play of hardware and software. In regards to hardware, we are in good hands, right? Because Mark and Paul bring us Hilbert with 100 qubits and later on 1,000 qubits and other players as well. And, the ability to run circuits for these scalable quantum computers is shifting from dream to reality. And also we see many organizations that want to do exactly that, right? In various industries, developing quantum software and running them on various machines, getting ready for quantum advantage. But the problem is currently, as we said before, this is very challenging, right? With existing tools and methods, it's very reasonable to design toy circuits for 5, 7, 10 qubits. It's already very challenging to do that for a few dozen qubits. And it's practically impossible to scale, right? To design in a reasonable way a circuit for 100 or 500 or 20,000 qubits. So current tools and methods are just not good enough. And I want to give one example. Maybe. Everyone who started, developing quantum software, so I guess you did this nice exercise, the Grover search, right? And basically the Grover search algorithm, so it's built of 3 main blocks, and the more complex one to program is the oracle. You need to design the oracle that will mark the relevant states. In this case, it's simple, right? You want to mark 2 states out of 8, and that's doable. It could be hand-coded in the gate level, only with a few gates. But what if you want a more complex oracle? Let's say that you want to define 3 quantum registers, A, B, C, and we want them to apply to this arithmetic expression, to this arithmetic oracle, A plus B plus C and 15, so on and so forth, equals 4. So this is complex, right? This is complex, and, spoiler, this is how the circuit looked like. This circuit was automatically generated with the Classiq platform, and each of these boxes are functions. Each of these functions has internal functions, and it's already quite complex. But this is small, right? This is on 22 qubits. And now we want to scale. We want to scale to hundreds, thousands, and more qubits. So basically, that's what we do with Classiq. The Classiq platform enables you to define a high-level functional model of the circuit, defining only the functionality you want to achieve and the hardware constraints. And then the synthesis engine synthesizes a gate-level circuit that meets your demands and constraints. And before I finish the presentation, maybe I give one industrial case study, one example. So one of the optimization problems could be solved with quantum computer is a 3-SAT or K-SAT optimization problem, which is good for several use cases. One of them is for formal verification. So what you see here, this is actually 4-SAT, and the important part of the model is this one, describing what constraints you would like to achieve here. And then when you synthesize the quantum circuit, and I hope you'll see it, so you get, and it was synthesized with the platform, you get quite a complex circuit, right? I hope you see it right now, but basically, this is a circuit that you wouldn't want or can to design manually. Each of these boxes are functions, you can open them, and it's quite complex. And this is for 77 qubits, right? Now, I think we all understand the problem. We now understand, part of the solution, and it's super exciting for us to be partnered with ColdQuanta, who really brings, these exciting machines to reality.
Thank you very much, Nir. So moving on sort of to the meat of the presentation. So the first topic is, why should I care? Why should someone care? What can you do with 100 or 300 or 1,000 qubits that you cannot do today? Mark or Paul, perhaps you want to take a crack at this first?
Yeah, I think these questions are quite closely interrelated. And why should I care? And why should I care now? I think ultimately, as we think about the kind of classes of problems for which quantum computers will enable us to obtain real business value, and certainly real business value, let's say, in the near term, examples like quantum chemistry, for example. So to be able to model, say, a molecule like penicillin, several hundred, I think that the numbers in the kind of high 200s, low 100 number of 300s of qubits. And those are the kind of problems where we start to see real business benefit. And so the question of why should I care is ultimately one of scaling. And certainly there's a wide variety of problems where we can look at potentially needing thousands, tens of thousands, maybe even hundreds of thousands of qubits. And the reason I say it's intimately tied to the question of why now, I think as with any learning curve, quantum computing will have significant benefit for early adopters who are able to climb the learning curve as the technologies mature. And so we expect to see a kind of a co-development of the use cases with the algorithms, with the hardware, as we seek to solve these problems and really deliver exponential value for businesses. And I think the same is true. I was listening to a conversation earlier today about the parallels between the evolution of AI and the evolution of quantum computing. And certainly there are numerous examples we can point to in industry and whole companies and businesses that have been created through the use of deep learning and machine learning as that technology evolved, and examples of companies that got left behind and are struggling to keep up and climb that learning curve. The same thing will be true in quantum. So there is a real return to value in adopting these technologies now, even if we're still in the reign of, say, 100 qubits. Pretty soon, we'll be beyond that into many hundreds and then thousands. And so there's a real opportunity, as I say, to get on that train, climb the learning curve, and now is really the time to engage.
Yeah. Let me go ahead and follow up on that and really try and respond to the question of why now. There's been a progression. If you look at the history of the hardware available for quantum computing, the field is about 25 years old. 25 years ago, we saw the very first gate operations on pairs of qubits. And at that time, the community was working to answer the question, is this even possible? Is this a dream, or can we really perform quantum computing? And that question has been answered with a very clear yes. And one of the next questions that emerged in the following decade or so was, well, we can do this with a pair of qubits. Can we really scale this up to many qubits? And again, I think with several modalities, the answer to that question is also a very clear yes, that we can scale up. But we're now in the era where we're starting to see 100-qubit scale devices deployed. And maybe I'll go ahead and just share a screen right now and think of this as a complement to what Nir showed. See if I can turn this on. And I'll show you a picture here of, part of why we're so excited about this cold atom approach is that we now have in our prototype machines arrays of more than 1,000 qubits. And so what you see on the background here is a real image of real atoms arrayed in a two-dimensional grid. So this is over 1,000 cesium atoms. And for scale, you can see the size of a human hair there. So although the Hilbert machine that ColdQuanta is bringing online this year will be a 100-qubit scale machine, we already know, based on work done in Madison, that we have optical approaches in place that are working that give us a very clear path to 1,000-qubit scale and even beyond 1,000-qubit scale devices. And so we're in this era now where we are very close to being able to control and run circuits on this very large numbers of qubits And so we need to think very closely about, well, how do we combine that emerging hardware capability with the capability of actually programming the circuits and implementing algorithms.
And Mark, you're also a professor at UW-Madison, right? And you've been doing this for quite a few years. Have the applications changed that when people were speaking with you 10 or 5 years ago, do they think about what to do with these larger computers differently than they do today? Or the applications have always been the same, but now the hardware is actually catching up?
I think the focus of the field has evolved over time, and it's not been a linear path. The original insights from Feynman and others were to use controlled quantum systems to simulate naturally occurring systems that we weren't able to simulate on our classical computers. So really quantum simulation. And then the field had a big push starting in the early 90s with Shor's algorithm and factoring and cryptographic and security applications. But I think to a large extent, the field has swung back, looking at the quantum simulation applications in terms of quantum chemistry, ab initio calculations of chemical processes, design of functional materials, and then also the new direction that has become very important is using quantum machines as an alternative to classical machine learning and artificial intelligence, which has become so important in society over the last decade and more. I remember when I was a graduate student, I worked on optical approaches to machine learning. And at the time, these were experiments, but it wasn't widely used with classical computing hardware because the computing power was not there. With the evolution of classical computing power, machine learning and artificial intelligence has assumed much increased importance and widespread use. And I think we're going to see the same with quantum enhancements to machine learning as we go forwards.
One of the interesting things to me about hundreds of qubits is that all of a sudden you go past the capabilities of simulating those circuits on classical machines. I think for a fully entangled system, you can think about 50 qubits as sort of the threshold where a high performance computer can no longer simulate, a quantum algorithm. And all of a sudden, if you have 100 or 300 or 1,000 qubits, do you think that there will be just the same algorithms, just bigger, the same applications, just a little bit more? Or what do you see as happening when we have larger number of qubits, and how do we work with them?
First, I think these are good trouble, right? If we could simulate it, it would have been fun, but not very helpful. So I think, it is an exciting new era. Some of the algorithms are scalable, right? Some are, mathematically proved to be scalable, like the Shor's algorithm, like the Grover algorithm, and some are heuristics. So, for VQE, for example, today we can simulate small molecules with a very small Hilbert space, but we don't really know if it will, scale to exponential or any other speed up on large machines. So it is yet to be seen. But I think, if you tried to have a conceptual experiment back then in the 60s, and you would ask yourself, what can I do if I had a computer chip with billions of transistors? I doubt it if you had invented Google or Facebook or the internet, because when you do it, when you try it, when you develop the software, when you run it, when you run the circuits, you can, push the limits of what we can imagine today. So existing algorithms, every one of them is a revolution, but hopefully many more are yet to be discovered.
I want to ask you all about quantum advantage, sort of a goal that's been discussed. When can companies get to quantum advantage? When can they do things that are truly useful to business? But before I do that, Nir, there are a couple of questions from the audience about the demo that you showed on the SAT problem. So two quick questions. One, is there you mentioned an industrial usage for SAT? What would that be? And the other is, what do you think the speed up will be? I mean, a 3-sat problem is NP complete. So is a quantum computer only offer linear speed up? I mean, how do you think that scales?
Yeah, fair questions. So first, the K-sat problem is relevant for several industrial use cases. One of the most famous and most useful is in the formal verification process of classical hardware, classical chips. And yes, indeed, it's an exponential hard problem, anti-hard problem, and the algorithm that I showed is Grover-based, so it brings only quadratic speedup. The reason I showed this example is not necessarily because this is the killer application. By the way, even a quadratic speedup could be very relevant because today, obviously, these algorithms are being used and we don't solve them optimally, but we have many heuristics. So if we could go beyond these heuristics and get better results, so even this speed up could be relevant. But the more interesting thing in the demo was showing how you can define functional model, very simple constraints, and then the hard work of the generation of the circuit is automated. I hope it answered, but I would love to elaborate later on.
Thank you. So, Paul, what do you think about quantum advantage? Or at what point do quantum computers become more than an experiment and move into the realm of a true business tool that delivers true business value?
Yeah, I think the concept of quantum advantage, I think one of the misconceptions, maybe kind of generally in the enterprise world, is that it's a light switch that will flip on and all of a sudden we'll kind of be in the promised land. I think the reality, though, is we'll see quantum advantage delivered in different ways, in different applications, in different verticals at different times. And so, for example, there's been some recent research that suggests provable quantum advantage in using a quantum computer to process data from quantum sensors. And that's obviously a very important topic for ColdQuanta as we play in both of those markets. And naturally, if you want to explore the Hilbert space of a quantum sensor, the best way to do that is actually with a quantum computer. And I contrast that, for example, to the other topic which tends to be front and center in the public's mind, certainly in the popular press, which is the possibility of a quantum computer breaking public key encryption. And for us to reach quantum advantage there certainly is much further down the line. So I think we have to be careful when we talk about quantum advantage to really differentiate the use cases because those will have different applications and different timing requirements.
So some of the use cases have been apparent for quite some time, but yet until recently, we didn't have quantum computers with more than a few dozen qubits. So let's talk about why is it so difficult to get there? I mean, Mark, you've been at it for many years. Don't you just leave the qubits like rabbits and they multiply? I mean, what's the difficulty in getting to hundreds or thousands of qubits? And then Nir, maybe you could discuss the same thing about would it be difficult to write software for large quantum machines?
Sure. Well, there's an interesting but also very exciting challenge that's intrinsic to developing a quantum computer. And it's based in how different they are from classical machines. The key quantum phenomena that are at the core of the enhanced processing capability of quantum computers is superposition and entanglement. And so building a large quantum computer that relies on at-scale superposition and entanglement is akin, if you will, to keeping Schrodinger's cat both alive and dead. David Wineland, who won a Nobel Prize for controlling quantum systems, likes to refer to it as raising Schrodinger's cat. And you're not going to run into Schrodinger's cat on every street corner. Raising one is very difficult because it requires both controlling the quantum world with extremely high precision and at the same time keeping it isolated from the environment, which causes decoherence. So this is a grand challenge, perhaps the hardest challenge that anyone has ever set for themselves. So it's not a simple task, and it takes deep understanding, but also deep technology and engineering in order to be able to deploy a quantum system. And part of the reason why we're so excited about this atomic approach beyond the scalability is that these are nature's qubits, single atoms acting as single qubits. We don't have to engineer them. We don't have to build a fab. We're given them essentially for free by nature. We have to build the classical control system around them to make the computer possible. But we see that as a grand engineering challenge, not as a new science challenge.
So how far are you along, Paul? I mean, how is the project going? When can we touch a 100-qubit computer? Or is it something that as soon as you touch it, you figure out if it works or doesn't work? You force it into a certain state.
Yeah, so I would say if you try to touch one of our quantum computers, you probably make our engineers and physicists rather angry. But the real answer to the question, we'll be releasing our first commercial quantum computer here in the next few months. And as Mark mentioned before, that will be a 100-qubit scale device. We'll initially turn on a smaller number of qubits as we optimize and continue to enhance the software. But ultimately, that will very quickly scale to the 100-qubit realm. I will say, though, even prior to that, with one of the prototype machines in Mark's lab in Wisconsin, we were able to demonstrate for the first time a multi-qubit, multi-circuit gate on a cold atom quantum computer. So that was an important milestone, obviously for us as a company, but I think an important milestone for cold atom as a modality, and certainly expect to see that scale very rapidly from here.
When you mention modalities, I mean, obviously there are other modalities. There's superconducting, they're cold atoms, spin, optical, so on and so on. Other than the question of which is best to scale the computers, do you think that one type of modality might be better suited to certain applications than others? I mean, would I be in a situation where to run QML, I would use one modality, and to run chemistry simulations, I would prefer something else?
So I think the simple answer, and Mark may well have a more insightful answer than mine, but I think the simple answer is at this point, it's still very early, right? We're kind of day one of the quantum computing industry. I think one of the areas where we may well see different modalities play out is to one of the questions I think that kind of came through in the chat about, for example, where does quantum play in the world of autonomous vehicles? Do you have quantum computers that are actually mounted on a mobile platform? You probably won't have a million qubit superconducting quantum computer ever on a mobile platform by virtue of the requirements for size and cryo refrigeration. You may well have other modalities, and cold atom would certainly be one of those, where you could develop a much smaller form factor and maybe smaller number of qubit device that acts as an accelerator as part of a process that's useful in the environment of autonomous vehicles. So that may well be one of the areas where we see different modalities playing out for different kinds of applications.
Nir, I can write probably a 10-line Python program with relative ease, and I would thus believe that if I can write a 10-line program, I could write a 100-line program or a 1,000-line program. Why is it different with quantum computers? Why is it that if I can use some platform, some language to create a 5-qubit circuit, that doesn't imply that I can tomorrow create a 500-qubit circuit?
First, I invite you to try, and then my answer will be irrelevant, but I'll try to answer anyway. So, okay, yes. So basically what you do when you develop quantum software today is to design or to describe a quantum circuit, one quantum circuit. You need to know perfectly well which quantum gates to apply on which qubit, what building blocks to use where. But basically, out of a huge design space of possibilities, you need to choose one with no automation at all. And you need to take into consideration many design choices and challenges like auxiliary qubit reuse, and or the order of local Hamiltonian terms, and so on and so forth. There are so many design challenges, and this is doable when you do that in a very small scale. But when you try to scale, you have two problems. First, it's challenging. It takes a lot of time. Even if you know on which hardware you're going to run, and you know for some reason how to embed all the hardware constraints into the quantum circuit, then the problem is that you probably designed it in the naive way, right? And probably if you succeeded to create 500 qubit quantum circuit with the right automation, you could do that maybe with 100 or 200. And, it could be 2 years difference between, now and quantum advantage. So I think these are the main reasons, and, abstraction is needed and automation is helpful.
Yuval, if I could go back to your question about, are there different problems that are better suited for different modalities? In part, that's going to be the case, but I think it's as much a question of the software being optimized for different hardware architectures. Just yesterday, I was reading some work out of Berkeley, a team headed up by Umesh Vasarani and Norm Yao, who were talking about the potential for quantum advantage at intermediate scale. And interestingly, in this work, they presented two different algorithms for reaching demonstrable quantum advantage related to interactive proofs. And one of the algorithms was optimized in terms of the number of qubits, minimizing the number of qubits. And the other algorithm they gave for this problem was optimized in terms of minimizing the number of gates. So depending on your hardware that you have available, you want to have software that allows you to implement these algorithms in a way that best matches the hardware capabilities. And I think that's going to be very crucial as the field advances.
I think that's a great point. And some of the questions we're getting from the audience have to do with noise and error correction. And noise might limit the depth of the circuit. How long can you run within the circuit? And so, Nir, would it be correct to say that if I had more qubits, such as from Paul, we could have shallower circuits that maybe run better than circuits that have fewer qubits but are longer?
Yeah, first, it was so fun so far. I wonder why talking about noise, but now that's okay. That's important. So yes, definitely. This is one of the trade-offs you can control if you can explore the entire design space, right? Because you take two circuits. One uses 100 qubits with specific depths. The other one could triple the depth, but it uses only 50 qubits, right? So one could be relevant, one is irrelevant, but you can't really do that manually. What you can do with our platform, for example, is to define the constraints, right? I do need it to work on, 70 qubits with no more than 500 CNOT gates, and so on and so forth. And then automation, explores the entire design space. And yes, very different circuits could meet the same functionality. Most of them are irrelevant for a specific machine.
So the Berkeley team, I don't think they used Classiq platform, but had they used the Classiq platform, maybe they would get an even more compact circuit or a more optimized circuit, right? You mentioned design space. Could you just explain what it is for everyone's benefit?
Yes, definitely. So you have many design choices, and the fact that if the very same functionality could be achieved with billions of circuits, right? You have so much flexibility in this imaginary space. And when you design quantum circuit today with, Qiskit, which is fantastic, it's super important programming language. So you choose one. You need to design one circuit. You need to take care of all of these design choices, and to design one. And maybe you chose the optimal one, but this is very much unlikely. Exactly as it's unlikely for you to do compilation manually, right? You trust the compiler to automate compilation, but the compiler is quite limited with its flexibility because it's got its input a gate level circuit and it needs to keep the gate level functionality. So it's, it does a lot of work, but it's limited. If you give automation the freedom to choose the right design choice, you can get much, much better results, yes.
So let's assume I'm a financial institution and I'm doing portfolio optimization, and I just want to optimize a greater number of assets than I can. What's the best way for me to know how many assets could I optimize on a 100-qubit machine or a 200-qubit machine? Or in other words, Paul, maybe you could take that. How would I get started in understanding whether an upcoming ColdQuanta machine can help me do the job?
Yeah, I think one of the aspects that Mark was mentioning before in the answer to the question of the different modalities also has a part to play here, because the range of capabilities that are available to you in writing your algorithm on one type of quantum computer may well be different from another. So, for example, in the cold atom computer that we're building, entanglement and connectivity are very different from what would be available, say, in other devices. So ultimately, our approach will scale over time to very high connectivity. So you may be able to have 50 to 1 or 100 to 1 connectivity, and that's going to open up a range of possibilities in terms of algorithm development that maybe are not available on other platforms. So the question of how do you solve a particular problem, how many assets could you optimize, will be as much a function of the platform itself and the innate capabilities of that platform as it is the attendant software. And so certainly I think what we'll expect to see happen over time today, to your question that you asked Nia before about writing a 10-line Python code and how would you scale that up, we're kind of essentially at the same point that we were in the classical computing world when we were writing machine code, maybe assembly level code, right? And so today, if you're a hedge fund manager or a portfolio manager, you're not doing your optimization by writing machine code or assembly code. You're writing in a far more abstract way, utilizing packages and utilizing functions that enable you to do that optimization in a more modular fashion. And so expect to see the same thing happen in quantum, taking advantage of the power both of the algorithms, but also the underlying capabilities of the platforms. And certainly at ColdQuanta, while we're pushing on qubit count, and that's the headline number that everyone talks about, equally important for us is extending that connectivity because of the range of capabilities that will offer to the application developers.
So if I developed an algorithm for 200 qubits and I ran it on your machine or on someone else's machine for that matter, how would I know that it actually works? How do I debug something where it's difficult or impossible to put breakpoints and everything is entangled together? Nir, could you address that question and maybe Paul or Mark after that?
Yeah, sure. First, it's a tough one, right? It's indeed a great challenge, and we take two different approaches. First one is explainability, right? Explainability of quantum circuits. Probably you saw that the circuit that I was showing before, it was complex, but it was functional based, right? You could understand what are the blocks, what are the functions, and of course, a lot of work is to be done on explainability, but this is one direction. Other directions are, yes, not putting breakpoints, but stopping the circuit at different stages having the statistics and as it's kind of reverse engineering in a way. There are several methods over there. We are very far from having one method that is here to stay, but a lot of work is being done, and obviously that's a great challenge. And yes, we'll see.
I'll just add that I think perhaps one of the best ways of evaluating the performance of quantum computers and continuing to do so at scale is just in terms of algorithm performance. And there I can point to the QEDC benchmark suite, where they had a range of present algorithms were tested on different hardware platforms. And certain algorithms, even at scale beyond what can be classically simulated, it's possible to look at the results that come out of the quantum execution of the algorithm and see if it makes sense. I mean, I think the classic example of that would be the factoring problem, where that's an NP type problem, so it's easy to check a possible solution. And so we need ideas like that to continue to test quantum computers at scale.
In my experience, that's one of the reasons companies are getting into quantum right now, because even though the computers may not be large enough today as we record this to deliver fantastic business value, they do need to gain the confidence and the expertise. They might say, yes, we can balance this portfolio on a classical algorithm. Let's see what the quantum one does, and then gain confidence that when we do have larger number of qubits available, machines with less noise or with higher connectivity and so on, then we actually can trust the algorithm even more. On the question of noise, one of the because of noise, and I know Nir doesn't like me to bring noise up, but this is where we live in these days. Most of the useful algorithms are hybrid algorithms, right? They have part classical and part quantum, the optimization algorithms and so on. So I wanted to ask all of you, maybe Paul from your side, how is access to cold quantum computer, how is it done? And is it easy for an enterprise to implement a hybrid algorithm that uses some cloud resources that they may have on Azure or AWS or Google together with ColdQuanta? And then after that, Nir, maybe you could reflect on, is it possible, is it easy to write hybrid algorithms with the Classiq platform? So go ahead, Paul.
Yeah, I think there's a near-term piece to that and maybe a slightly longer-term piece. And the near-term piece is Hilbert, our first commercial quantum computer, will be available as a cloud service, initially through our own cloud platform, and then shortly thereafter through a number of the commercial cloud platforms. And I think that though the reality is today, if you look at the quantum cloud platforms, these are platforms where the QPU is not physically co-located with the classical workload. And so when you're running hybrid algorithms, part of that algorithm is running on the classical computer. So in a VQE algorithm, for example, part of that's running classically, part of that's running on the QPU. And there are a variety of techniques that are emerging to try to obviate the delays and the challenges that introduces. I think longer term, we'll ultimately have to see the QPU physically co-located with the other parts of the workload, because these applications will, as was said before, ultimately be hybrid algorithms. And an enterprise will have a problem to solve, and they won't much care which part of that problem is solved with a quantum processor, which is solved with a GPU, which is solved with a TPU, or a CPU for that matter. They'll just want the problem solved. And I think that is one of the powers of the cold atom modality approach, which is ultimately the miniaturization, the ruggedization, and ultimately the deployability in an exascale data center environment.
And Nir, to the other question, is it difficult? Is it possible to write hybrid algorithms with the Classiq platform?
Yeah, definitely. So, of course, we support VQE, QAOA, and others hybrid algorithms. But maybe another important thing here is, of course, noise is important, and error mitigation, error correction are important. And the beautiful thing is that when you define a functional model, you can embed the hardware noise model as constraint, and then in the process of the circuit generation, the synthesis engine takes into consideration the many hardware characteristics, connectivity, and so on, but also the noise model, and then you get from the first place a circuit that is adapted to this noise model and handles in the best possible way the noise. So obviously it's relevant mainly right now for NISQ, but later on it will be even more important with error correction.
So the Classiq platform could adapt to noise model and connectivity model depending on the constraints that you're entering into it. Is that correct?
Yeah, that's correct. You design a functional model, what functionality you want to achieve. You don't need to tailor-made the circuit for each machine. But then if you do know on which machine you're going to run, you are going to run it on Hilbert. So you can embed Hilbert's noise model into the high-level model, and you get a circuit that is adapted to its characteristics. Yes.
Now, given, and maybe Paul will want to cover his ears for this question, but given that there are various vendors, various modalities doing quantum hardware, how important is it for an enterprise to be able to have sort of hardware elasticity, to be able to say, yes, I run it on ColdQuanta, but I also want to test it on Honeywell, or I also want to test it on someone else's computer? Is that important? Is that feasible?
First, yes. Not many hardware vendors provide users with 100 qubit machines today, but definitely users do want to experiment. Everything right now is exploration. So yes, on our platform, we support also Azure Quantum, AWS Bracket, IBM, and so on. And at some point there will be a winner or several winners, and it may change. But currently, it's exploration. It's yes.
I mean, actually, Yuval, I think this goes back to how do we continue to develop leading technology platforms? One does it by testing different approaches to solving the same problem. If we have a quantum computer at scale that cannot be verified classically, well, let's try and compare two different quantum computers against each other and see if they give the same results. The same thing happens today, for example, in the world of atomic clocks that also use these perfect natural atoms. How does one verify that we've built the world's best clock? Well, you build two of them and you compare them together. And I think the same kind of approach will be needed in the quantum computing world.
There was a question from the audience about the patent space. I would imagine that ColdQuanta has and is filing additional patents on some of aspects of your designs. I know that Classiq has filed several patents. But as you think about the end user, the enterprise, how important is it to develop IP and file patents before the space is completely saturated, in your opinion, for an end user?
Is that a question to me, Yuval?
Anyone who wants to jump in, not all at once.
Yeah, I mean, I would say, and I'm certainly not a patent attorney. I think the real focus, and you're quite right, with filing various patents at ColdQuanta, but the patent is not the objective. The objective is innovation, and the purpose of the innovation is to move forward the state of the art and ultimately to deliver these large-scale devices that provide useful value for customers. And so patents are obviously a way of protecting IP. They're a way of building the IP portfolio. But really, the fundamental focus of ColdQuanta is to innovate and to move forward in building these large-scale devices that ultimately will solve some of the world's hardest problems.
Three of us are wearing jackets right now. except Nir. So I wanted to ask you about quantum winter. Based on your interaction with customers, what you're hearing, the amount of interest that you're fielding, is that something that you're worried about, or that's past tense and not worried about that anymore? Nir, would you want to go first since you're not wearing a jacket?
Yes, in Israel, we already had the 3 days of winter we have every year. So I guess summer is here now. I think that you see this almost arms race. You see all of the giants there. You see it's not hype, it's reality. It's business reality. It's hardware providers, enterprise adoption, governments, huge budgets. But most of all, you see the progress. You see the technical progress in hardware, in software. You see an industry, a maturing industry. And I think that it's going to be incredible, very surprising if we're going to see significant quantum winter. It may take time. It's okay. I'm the last one to tell anyone that in 2 months they will see any quantum advantage. Maybe next year, maybe in 5 years. I don't know. No one knows, right? We are all trying to make it happen soon, but I really don't see a quantum winter coming.
Yeah, I'll add to that. I think a couple of things. I think number one, I absolutely agree with Nir's comment. I think the rate of progress, demonstrable, provable progress, is really astounding in this industry. It's actually, even as an industry participant, it's hard to kind of keep up with the level of progress. So I think that's point number one. And I think the active engagement we're seeing from the end user community as well is testament to the fact that progress is really being felt and that there's real promise in the very near future to actually start to solve some real problems. I think number two, though, at the same time, as industry participants, we do have a responsibility to talk in a very clear and transparent way about both the promise of the technology, but also the challenges. And there is certainly a fair amount, I would say, in the popular press that is overhyping the potential of quantum. But by the same token, I think in many ways we're actually underselling the true promise of quantum to, again, solve some of the world's hardest problems, to transform industries. Certainly one of the areas kind of near and dear to our heart is in climate change. And it's in many ways hard to overstate the impact that quantum in the broader sense will have in that area. So I think there is a responsibility that comes along with our place in this industry. But no, I certainly don't see a quantum winter on the horizon.
There are a couple of questions about Mark's setup and the beautiful picture of all the qubits that you showed earlier. But before we get there, I do want to ask Nir and Paul, how does one get started? So I'm an enterprise. I listen to this. I'm excited about the potential of quantum. I understand the limitations of some of today's system. I'm excited about this next generation of computers and software. What do I need to do to start thinking about using a cold quantum computer? And Nir, what do I need to do to start using Classiq software?
I'll jump in on that one. Hopefully, in the invite to the webinar, we have contact information there. Get in touch. We'd love to talk with you about the problems you're trying to solve, about the objectives you have for quantum, and how Classiq can help together with your path towards employing quantum in your business. And we're actively, certainly, talking to early prospective customers for Hilbert right now, and would love to engage in conversation.
Yeah, definitely. It's definitely not too early to adopt quantum computing, but it's also not too late. This is a great time. You just need the right partner. Here you see two fantastic partners that are also partners partnering with each other. And contact us, and as Paul said, we'll understand what are the problems that you want to solve, and very soon you'll just be able to do that by yourself. You need no one. Use the Classiq platform to design complex circuits. You run them on Hilbert, and you are good to go.
So if I'm new to the industry and I actually want a career in quantum computing, where would you have me go other than UWM? I think Mark, you have a wonderful, I think it's a 1-year course on quantum. Is that correct?
That's right. We have a professional master's degree in quantum computing.
Excellent. But Paul and Nir, where would you advise someone who wants to get into quantum? Where should they start?
Well, I mean, wanting to get into quantum covers a wide variety of disciplines, right? I mean, if you want to get into quantum from a business perspective, or from a software perspective, or from an engineering perspective, there's a variety of different paths. I think one of the really exciting things about quantum is that there are so many communities of interest out there for all of those disciplines. You can get involved in learning to program. You can get involved in learning the business aspects of the industry, the physics aspects of the industry. So it's really a function of where your interests lie. And if you want to make a career out of quantum computing, then I think the obvious answer to that is the email address is here on the screen as well. I know both companies are hiring in a wide variety of areas, so we'd encourage you to get in touch if a career in the industry is of interest.
Absolutely. Nir, is there something you'd like to add to that?
I just can't. It was perfect.
Very good. So Mark, people are really curious on the chat. What's the connectivity between the atoms that you showed? Are you using commercial lasers to hold them in place? What kind of laser? What's the wavelength? What's the beam size? I mean, give us the recipe as much as you can before the IP lawyers jump in.
Well, those are all great questions, and I think we'd need another webinar to really address them in any detail. We do have some more technical webinars that you can find actually on the ColdQuanta website from earlier presentations. But in a nutshell, this atomic approach to quantum computing is very simple. You start with atoms, and we get those for free from nature. You put them inside a vacuum cell, and Paul showed you a small ColdQuanta vacuum cell earlier. And ColdQuanta is really a world leader in producing pristine vacuum conditions with excellent optical access in a very small footprint. And you add to that some optical subsystems, some lasers, some control electronics, and a good dose of software. And you put all those pieces together, and you have the makings of a quantum computer. The details of the fidelities and the connectivity and the coherence times and so on and so forth, I'd love to speak to, but I think we're running out of time today. But please get in touch with us, and we'd be happy to engage with more information.
I mean, you make it sound relatively easy, but as we say in Classiq, if it was easy, we'd have marketing do it. So as the chief marketing, the one who's got the easy job in Classiq, I wanted to thank the three of you, and I wanted to thank the audience for joining us today. We'll have a recording on the website shortly, and please join us for future events. Thank you so much for being here today.
Thank you.
Thank you.
Thank you.
All right.